This is the lecture for Part B of Module 1 of Unit 3. Concerns determining rate laws. We've seen what the form of rate laws looks like. Now let's consider an example of determining rate laws. Okay, we consider a reaction. Here we have a reaction in which CH3CHO, an atmospheric pollutant, decomposes to CH4, methane, and carbon monoxide. The rate law must be R equals K times the concentration of CH3CHO to the N power. We've seen that in the last, in the last lecture, in the last section. K is the rate constant. N is the order of the reaction. We're told the initial concentration of CH3CHO is 0.0363 moles per liter, and then we're given two rates. One when 5% of the material has reacted, and another rate when 20% of the material has reacted. The question, or typical question you may see for a type of problem, is what is the rate law? If R equals this expression, or if this is the expression for the rate, what are the values of K and N? The important thing in a problem like this is to recognize that what you have is rates, more than one rate, for various concentrations. A good first step is to take the two rates we have, or the two concentrations we have, the two situations we have, and find the concentration for each. For example, when 5% has reacted, 95% is left. So we can find a concentration when 5% has reacted, 0.0345 moles per liter. And likewise, when 20% has reacted, that means 80% is left. And we can multiply that by the starting concentration of 0.0363 moles per liter to get 0.0290 moles per liter. Right, so we had, again, two situations, and we now know the concentration for each. We were given the rates within the problem at those concentrations, 1.07 mole times liters per second, and 0.076 moles times liters per second. Allow me to emphasize again here that the units of liters and seconds are in the denominator and moles are in the numerator. We have two rates for two concentrations, and we can, at each rate, we can write R is equal to K times the concentration. The actual concentration appears in brackets to the N power. What happens then is I just divide R1 by R2. Right. Dividing 1.07 by 0.76 produces 1.41. All the units have canceled. If I divide the red expressions over on the right-hand side of the equal sign for R1 and R2, K's cancel, and 0.0345 is divided by 0.0290. Units cancel. And the result is 1.188 to the N. 1.188 is the result of dividing 0.0345 by 0.0290. Right. Classic way to solve for N in this case, and you'll see it again in another example in this unit, is to then take the natural log of both sides of this expression. Natural log of R1, R2 is the natural log of 1.41, which is equal to the natural log of 1.188 to the N. Property of natural log allows us to write this natural log of 1.188 to the N as N times the natural log of 1.188. In other words, the exponent can be pulled out front of the natural log and appears as a factor in front of it. This gives 0.344 is into the power of 0.172. We can then solve for n algebraically, and we get a 2. So this is a second order reaction. Right, determining k, we can simply go back to one of the two rate expressions, 1 or 2. I select 1, and I divide the rate, 1.07 moles per liter, moles times over liters times seconds, by 0.0345 to the n. This actually gives a value of 898 liters over moles times second. Just had to clear an arithmetic typo there. My apologies. Okay, make note of the units, liters over moles times seconds, which are arrived at by dividing moles over liters times seconds. Let me remind you again that liters times seconds is in the denominator, by moles per liter, twice, or moles squared per liter squared. Make note that these are the units, liters over moles times seconds, of second order reactions. Again, you will see that these are the units of second order reactions. All right, analyzing rate information. When you are provided rate and concentration for one reactant is, well, it's more straightforward than in the situation in which you have two reactants. Both the previous example and one we're about to consider are examples of the method of initial rates. And you are essentially dealing with that anytime you have information about a rate for a given concentration. Right, let's consider a case in which there are two reactants. 2 NOs and bromine gas react to make 2 NOBr. The rate should be R equals K times NO to the N and times bromine to the N, where M and N are the exponents, numbers that define the order with respect to each reactant, and K is the rate constant. Right. The kinetics of this reaction have been studied, and this produces the following data. Now consider the data you are provided. There are 5 experiments, and for each experiment you are provided a concentration, and while it is not exactly information about the rate, you know it's related to the rate, the change in concentration of the product with respect to time. Right. You will see that we can determine the rate law from this experiment, or these experiments. We can determine the orders, first the orders and then the rate constant. Let's begin by considering these experiments and determining the value of N. Right, to determine N, consider experiments 1 and 2 with the same initial NO concentration and different initial bromine concentrations. Rate is proportional to the rate of product formation, so the ratio of rates, R2 over 1, is 24 over 12, which we know, of course, will simply be 2. However, that is equal to 0.1, the concentrations of NO and Br2 from experiment 2 times the rate constant, divided by the concentrations from experiment 1. In other words, in the numerator of this expression we have the rate for reaction 2, from plugging into the rate law. And in the denominator, we have the rate of reaction 1. In this expression, k cancels, 0.1 to the n cancels, and we end up dividing 0.2 to the n by 0.1 to the n, which is simply 2 to the n. Alright, this means that 12 over 24, which is 2, will be equal to 2 to the n. The natural log of 2, then, natural log of the left-hand side, is equal to the natural log of 2 to the n, natural log of the right-hand side. And that is equal to n to the natural log of 2. Again, we can bring n out and make it a factor out front. If natural log is 2, it is n times the natural log of 2. N must be 1. Now, you may not need to have to go through this arithmetic process. If you see that doubling the concentration of a species doubles the rate, that implies that the reaction is first order. Right. Now that we have seen and discussed the determination of n, you should stop, look at the data again, and attempt to determine m before going on. The determination of m is very similar to the determination of n. Here we pick experiments 1 and 4 to look at with different initial NO concentrations and the same initial bromine concentration. 48 of 12 must be equal to the rate of 4 over a rate of 1. And that is, plugging in for the rate of 4, k times 0.2 to the m times 0.1 to the n, over, once again divides that by the rate, or put it over the rate of reaction 1. On this side of the equal sign, k cancels, 0.1 to the m cancels, and we are left with 2 to the m power. 48 over 12 is 4. So this yields the expression 4 equals 2 to the m. Alright, you may have seen at this point, or inferred, and certainly you might infer at this point, that m is 2. Formally, however, you can proceed by putting taking the natural log of both sides. Natural log of 4 is natural log of 2 to the m, which is m to the natural log of 2. And m is the ratio of the natural logs. And if you evaluate that, you get a 2. Alright. Keeping in mind that the 48 and the 12 are not actually rates, but are proportional to rates. They are the change in the concentration of NOBr2 with respect to time. You should stop and attempt to determine K before going on. The coefficient of NOBr in the balanced chemical equation is 2, so rate of change of NOBr concentration divided by 2 is the rate, according to what we have already seen. Right. So R must be equal to twice the value of the columns that appear in the table. The rates of change of NOBr concentration. This is important to understand because we can now use this information to solve for K. If we take experiment 1, R is 2 times 12, or is 24 moles over liters times seconds. And that's equal to K times 0.1 to the 1 times 0.1 to the 2. If you remember that each of the species in brackets has concentration of moles per liter. Taking the product of these expressions yields K times 0.0010 moles cubes times liters cubed. And we solve for K by dividing that 24 moles over liters times second by 0.0010 moles cubed over liters cubed, and arrive at 24,000 liters squared over moles squared seconds as the units for this reaction. Alright, now the overall order for this reaction is 3, 2 plus 1. And these are the units of a third order reaction. Alright, this concludes the lecture for Part B of Module 1 of Unit 3.